Okay. As I asked you just now, is why we need to solve differential equations at the first place. I hope many of you already know about differential equations. So, differential equations. Anything which varies with time can be modeled using differential equations. So, anything varies with time is known as dynamics. Okay, and that means it dynamically changes. And any differential equation which changes with time or whose variable changes with time is referred to as a ordinary differential equation or a dynamical system. Okay. So a differential equation can be of many types. However, this is the broader classification. So you have one, two. You have ODEs, that is ordinary differential equations, and another part you have PDEs, that is partial differential equations. Okay. So here you usually have a single independent variable, variable, whereas in PDE you will have multiple independent variables. Fine. Okay. So I hope you understand this. Okay. So I think you know that suppose y prime or dy by dx is given by 0.2x into y. Okay. This is the ODE you have. What is your aim? What is your aim? Our aim is to find y. How y looks. How y varies with respect to x. If x changes, y changes. Isn't it from this differential equation? From this differential equation, you can say y is depending on x. Y is depending on x. Y is depending on x. Okay. So I want to understand how y is depending on x. Okay. So through this differential equation, can you find what is y? I hope you can find, right? This is the easiest method. What you can do? Dy by y equal to 0.x dx. And then you can integrate both sides. Then you can integrate both sides to find what is y. Okay. So you can see, you can easily visualize that y is kind of an exponential function, isn't it? What should it be? Ln y equal to 0.1 x square plus the constant of integration. Okay. So what is y? Y equal to e to the power 0.1 x square e to the power c. E to the power c is some another constant. Let me write it as d. Okay. So you can see this is the equation. This is the y value. This is the function y which satisfies the given ODE. Agree? It's okay? Okay. Now, this ODE has infinitely many solutions, right? This ODE with this solution has infinitely many solutions, isn't it? It has infinitely many solutions. Yes. Many of you might be confused because in many other books, any mistake is there? X square by 2, right? So this ODE y equals to d into the power 0.1 x square has infinitely many solutions. Okay. But many of you might be troubled with this because in many of the ODE, what you have learned, everywhere they are saying about unique solutions. Okay, ODE has unique solution. Yeah, and ODE has unique solution. But why it is I'm saying that it has infinitely many solutions. Yes, it's because of the constant d. So you have the control over constant d. You take infinitely many of them, and you will get infinitely many such y solutions. Okay. Due to that, I am saying that this ODE has infinitely many solutions. Now, when can the ODE have unique solution? The ODE can have unique solution if you give an initial condition where it should start. Okay. Say you will say y at x equal to 0 is 5. y at x equal to 0 is 5. So y of x, you already know the solution d e to the power 0.1 x square. So y of 0 equal to d e to the power 0. Yes, that is d equal to 5 because this is given as 5. Yes, agree? So you can now put that y of x equals to 5 e to the power 0.1 x square, given that y of 0 equal to 5. Now this is a unique solution. Now this is a unique solution. Agree? Agree? Can you understand what is the difference between the infinitely many solutions and unique solution? So when you have an ODE, so this ODE equation, what happened? Okay, so the ODE I just mentioned to you, I think I missed the slide, isn't it? Yeah. Yes. So this ODE, which I am circling in red, has infinitely many solutions. Infinitely many solutions. Whereas this ODE, given that y of 0 equal to 5, this ODE has unique solution. I hope you understand the difference between them. Okay. So this is a conceptual question can be asked. Okay. So given these two ODE, which ODE has infinitely many solution, which ODE has unique solution. Okay. Fine. You can see that in red, I have not given the initial condition. I see initial condition not given. So therefore, it can have any value of d. You can take infinitely many solutions you will get. But on the right in blue, you can only take this initial condition. That means d, a particular value of d you will get, d equal to 5. So this gives you this solution, which is unique solution. So I hope you can understand the difference between the two. This kind of problems where initial condition is being given to you is known as the ODE problem, in which initial condition is being given to you, is referred to as yeah, as Mr. Jubin told, it is known as IVP, initial value problem. Okay. Now this is the initial value. Now there is another class of problems where boundary value will be given to you. Boundary value. Okay, boundary value, we'll see what it means. But those kind of problems are known as boundary value problems. Many methods are there, like shooting methods, multi-step methods to solve. But however, we'll not go that much deep in this course. Okay. Fine. So yeah, I hope you learned about integrating factor and all those things in your bachelor's. Integrating factors, separable ODEs, and all these things you already know. Okay. So directly we will come, we will not concentrate into the methods, what you have learned. I think you have learned about integrating factors. Integrating factors, integrating factor for separable ODEs. This is already you might have known, or I have in my notes if you want to scan. Okay. This is integrating factor for separable ODEs. Then I think you have learned about Laplace transforms. How Laplace transforms can be used to solve ODEs, isn't it? I hope those who have taken course in engineering math and all these things can know. Laplace transform, you can solve ODEs. Okay. There is another thing, that is methods of undetermined coefficients. Undetermined coefficients. So I hope some of you might have gone through these methods. And these methods, there is also recursive solutions to ODEs. That means you say this is the power series solution, that is power series. Yes, some of you might have learned this. Okay, power series solution. So you assume, because the differential equation can be a function, and what you do, you assume that this is the solution of in form of a power series, that is as a series of polynomial, infinite set of polynomial. And what is your job? Your job is to find the coefficients of that polynomial. Okay, using recursive process. Okay, to be honest, this method, and this method during my bachelor's time, like, yes, I was going to my bachelor's degree, and I had these three in my course. Okay, the course name was engineering mathematics, and these three things were there. Okay, and during that time, as you all do now, I went home. Okay, I went home because of holiday. And yes, in Odisha there was a cyclone that time, Phylline. Okay, I hope many of you might not be hearing, you know about it. So Phylline was there. So I took my book. I liked. Huh? Yeah. So during that time, flood was there. Okay, flood was there. It was known as Phylline. Okay, so to be honest, like it was 1 month break for us during that time, like holiday in our like institute. So I came home, and unfortunately within 2 days the flood happened. So during that flood, like you can't do anything. You have to sit in your home, and I had my math book, and I was practicing all this. Okay, so yes, there in that time, my mind was full motivated to learn these methods. But to be honest, it was very hard. Okay, maybe for this recursive power series, I start one problem in the morning, and I could complete it by 4 p.m. Okay, so 9 to 4, 9 a.m. I started, and it required a heavy patience. So these are the methods which can be done analytically, but are very hard. That I just want to tell you about my time when I was solving this method. Okay, but after that, I never came across this method. But it is good to know that there is a method like this where you can approximate the solution using power series. Okay. Fine. These are all analytical methods. That means you can directly find the solution y, the expression for it. But these are very hard analytically, to be honest. These are very hard analytically. Therefore, and many ODEs, they don't have analytical solutions. Don't have analytical solutions. So therefore, you can only resort to numerical methods. You can only resort to numerical methods. So how to solve ODEs via numerical methods. How to solve ODEs via numerical methods. Okay. So we will learn these methods. That is, we will learn Euler method in this class. We will learn about RK2, RK4 method. Okay. Then we will learn how to solve coupled ODEs, coupled linear ODEs, to be honest, not nonlinear ODEs. Okay. So these are the three methods we will learn in this class, and these are the heavy, powerful methods so far. Okay. So I hope it will be useful. Let's start with this. Of course, what is our duty? Like, what is our goal in solving ordinary differential equations? Yes. So I'll just give you an idea. For y prime, dy by dx equals to f of x comma y of x, given an initial condition like y of x naught equal to y naught. Yes, that means it is guaranteeing that there will be a unique solution. Okay. Suppose this is the solution. Suppose this is the solution y. Yes. So this solution is y of x. You can see that with variation in x, y is changing. And this solution is a solution of this ODE. This curve is a solution to this ODE. Why am I missing something? Am I missing something in this graph? Yes, I'm missing something because I told you y of x naught equal to y naught. So therefore, this guy should be x naught, where I am starting, and this should be y naught. then only this is the unique solution. Or else you can take one curve here, one point, starting point here. Okay. Now, our job is to find what is the next value of y. That means our job is to find what is the value of y at any given x. Say 2.5. Then what is y of 2.5? How can you find? Given the solution of this ODE. Yeah. How can you find? This is the idea. This is the idea. As usual, what we do in numerical methods? As usual, approximate. Numerical method is full of approximations. Okay, I never told you in any numerical method class that this is the answer. This is the answer. This is a solution, but it comes with some error. Okay, so it will be error can be 0.01, 0.03, but error will be always there. 10 to a minus 4, 10 to a minus 5, but error will always be there. So whatever numerical method schemes you have learned so far in your previous semester and this semester, it is an approximation to your original solution, to the analytical solution. It is not exactly equal to the analytical solution. Okay. So how can you find? See, what should be our general step? So given it y naught, how can I predict? So we need to have a step size. Okay. You are starting from x naught here, and I want to go here, suppose. Shall I go like this? No, right? I can go like this, but depends on my like strength and all this. Okay, I cannot go there by one step. Okay. So, yeah, there last bench. So what I need to do? I need to take small steps. So you can see x naught is here, 2.5 is here. It's very far. I have to take miniature steps. That is the step size. Okay, this is step size. So we can take a step size, say 0.01. Now, if you start with 0, no, this is 0.1 suppose, then your idea should be how can I compute at 0. So 0.1 step size you take. So 0.2, how much value will I have at 0.2? Can I find that value? So as a numerical method, people, like what you should do, you should approximate. You should approximate. How can you approximate? Draw a tangent. Draw a tangent. So if you draw a tangent, this is the tangent. Yes, this is the tangent. Now what you have to do? Just extend at x equal to 2.5, you need to find the value. So what you should do? Just take it ahead. Take it ahead. So it intersected here. So this is the value. What is your original value? Your original value is this. Your original value is this. But you got this as numerical method. So you can see the error here. The error is here. You got the idea? So this is what Euler method does. This is exactly the idea of Euler method. Okay. So how we are computing yi? Any ideas? So okay. What is the slope? The slope is the derivative of the function. Yes, derivative of the function. How can I write the derivative of the function? Y prime or dy by dx. What is dy by dx? This is the slope, right? Slope. Now I ask you, what is dy by dx? Already being given to you. Dy by dx is f of x comma y comma x. So dy by dx is nothing but f of x comma y comma x. That is the slope. Yes. Now, how can I write the slope? In terms of step size, y2 minus y1 by x2 minus x1. That is equal to y2 minus y1. What is y2? The future step. Y2 is the future step. That is yi plus 1 for some value. Okay, like future value. What is the past value? Y2 minus y1, yi divided by the step size. Step size is h, suppose. Because step size you do in one step, right? So can you tell me what is yi plus 1? Yes, this slope is evaluated at xi, yi, isn't it? The slope, you are evaluating the slope at this point so as to predict the new point. Okay. So through this method, see, through this simple observation, we derived the solution for differential equation or ODEs via forward Euler method. This is known as the forward Euler method. That means you are computing or predicting or approximating the value of yi plus 1, the future value, based on its past value yi. Okay, so this is the Euler method. This is the Euler method. Fine. Yi plus 1 is equal to yi plus the step size times the evolution of the function at xiy. Okay, so you can see just through one line we derived it. Okay, this is the simplest proof you can have. Okay. So I think yeah. So we'll solve one problem using this Euler ODE. Yeah. So the idea is solve like we have to solve this numerically question. You have this differential equation dx by dt equals to 1 plus x by t. Okay. Fine. Given that x of 1 is equal to 1. X of 1 is equal to 1. Yeah. Your job is to find what is the function x. What is x? Or maybe I can tell that use the step size h to be 0.1. Okay. And compute x of 1.3 using Euler method. Yeah. Can you do? Can you try to solve this using Euler method? So x is a variable which changes with time. X is a variable which is changing with respect to time. And I have given you the initial condition that at x equal to 1, at t equals to 1, x value is 1. So I am asking you what is the value of x at t equal to 1.3 using the step size of 0.1. That means you have been given time step 1. Then next iteration will give you time step what is the value at 1.1. Next will give you 1.2. Final will give you 1.3. You have to tell me what is this. Okay. Okay, let us solve this. Let us solve this. Okay. So you already know using Euler's method. You already know using Euler's method that what you already know. If dy by dx equals to f of x comma y, okay, fine. Then what is the how you can find? Our aim is to find y. Okay, find y. And how you can find y? Via iterative process. So that is yi plus 1 equals to yi plus h, the step size, times the right hand side of the equal to sign of dy by dx. That is f of x comma y, but you are solving at xi yi. So therefore f evaluated at xi and yi. Yes. Okay. This is Euler's method. Now coming to our question. Note this method we are applying here. Okay. Now instead of dy by dx, you have dx by dt. Here dx by dt means x is changing with respect to time. X is changing with respect to t. So yes, you understood dx by dt. So dx by dt and dy by dx are the same, nothing difference. Instead of y, you have x. Instead of x, you have t. Understood? That is just a notation change. There is no need to get confused over this. So coming back, now dx by dt equals to f of x comma t. What is f of x comma t? 1 plus x by t. Now, how can I use Euler method? Euler method, our job is to aim, what is aim? To find x, right? To find x. So therefore, your iterative method should be starting with x. That is x I plus 1, that is the future step, is equal to the past step as see the Euler method side by side, what I am writing. Xi plus 1 is xi plus the step size. What is the step size? H. Okay, times the right hand side of the ODE. Right hand side of the ODE is dy with whatever the differentiation right hand side of the equal to. What is the right hand side of this equal to of differentiation? Derivative 1, that is f. This guy is f. So therefore 1 plus, will you write x by t? Will you write x by t? No, you cannot write x by t. Then what value of x or what value of t you are going to evaluate? You have to evaluate at this value of xi. So therefore there will be an index xita. Yes, got the idea? Now what should you do? Put I equal to 1. Put I equal to 1. What you will get? X2 equals to x1 plus h into 1 plus x1 by t1. Yes. So x2 equal to what is x1? Given that you know x1 is x1 is 1, t1 is 1. Yeah. Yes. Good. Good. Ft comma x. That means you are understanding the notation right. So as Harilal told, x2 is x1 plus h into 1 plus x1 by t1. Okay. So what is x1? X1, yeah, please. X1 is 1 plus h. What is h? 0.1 times what? 1 plus 1 by t1. Yes. What you will get? 1 point x3, that is x2 plus h into 1 plus x2 by t2, right? So that is equal to, what is x2? 1.2 plus h 0.1 times 1 plus x2. What is x2? 1.2. What is t2? So what is this value? What is x4? What is x4? All should say. What is x? Like BJ you say. What is x4? Yes. x3 plus h into 1 plus. Yes. So what is the value? One plus. What the value? Okay. This is the final answer. Yes. So you can see, without even knowing anything about ODE, how to solve ODE, without knowing any analytical methods, just by computing function value and performing addition, you can find the value of y at a given value of x. This is why we need numerical methods for solving ordinary differential equation, where you don't need to have the knowledge of ODE. You understand? That's the idea. That's the idea. Given dx by dt equal to 1 plus x by t, how you find x? Using numerical methods. Given at any point, you go step by step, and approach to that solution. What is that value? Okay. Now, this method is the simplest form of the method, like simplest numerical method you can have to solve ODEs. However, there is an error associated to it. What is the error associated? What is the error associated? This is the error, right? This was the error. See, this was the original value, but your predicted value is this. So therefore, this difference is the error. This difference is the error. Okay, fine. Now that order, that error order is order of h. You can prove it. You can prove it. This error, what you are seeing, as I told you, numerical method can only approximate to the solution. However, it cannot reach to the solution. There will be always an error. That error is order of h. Okay, I will show you using Python. Okay, now, but the idea is the more the step size you do, the bigger the error. So therefore, it is depending on h. H we took 0.1. I suggest you take 0.01, but then you will have lot of steps. How many steps you did now? 3 steps. How many steps you did now? 3 steps. Where you started from 1 to go to 1.3, you did 3 steps because step size was 0.1. Now, if h is the step size 0.01, how many steps you need to do? 30 steps. So your calculation time will increase. But yes, you will get the accurate solution. So these 30 steps you cannot do manually, right? That you write a program for it, which can done using a for loop, so that it will continuously update the value of y, the iterative value, and give you the solution. That is the idea. Okay. So therefore, if you take h equal to 0.01, your error will be less because your error is order of h. Your error is order of h. So h is small, error is small. H is big, error is big. Okay, got the idea? So therefore, I suggest you take h equal to 0.01 and then h equal to 0.1 and plot the solution. You will see the difference and plot the actual solution. You will see for h equal to 0.01, your approximate solution will be very close to the original solution. Okay, whereas in h equal to 0.1, which you did, it will be a bit, the error will be a bit bigger. You got the idea, I hope. Maybe we can see it in Python. Yes. So you can see this explicit Euler method. So what I am trying to solve here, can you tell what is the function value? What I am trying to solve here? What I am trying to solve? Look into the code and tell me what is the differential equation I am trying to solve numerically using Euler method. What is the differential equation we are trying to solve? Tell me the ODE. Tell me the ODE. D. This is reverse engineering. Just by looking into the code, can you identify what is the ODE being used? So that you know, if you understand Euler method, you can just tell what is the ODE by looking into the code. Okay, we'll start. Anyway, so you can see I am defining the parameters, that is lambda t. Lambda you use for a function. Yes. So t and s. So f is a function of t and s. F is a function of t and s. And that is being given by e to the power minus t. Okay, we'll see what is that. Okay. There is no s I'm seeing here. It is a function of. Anyway. So h is 0.1 is the step size. Okay. And this is the numerical grid I am planning, like np.range 0, 1 plus h, h. Okay. So s naught is the -1, that is the initial condition. And this s you want to find. You want to find s because s is varying with respect to time. So it is ds by dt equal to e to the minus t. Some maybe constant is there. K e to the minus t something. Yes. You are trying to solve this ODE. You want to find what is S. What is S? Okay. So this is your f of s comma t. Fine. Okay, got the idea. So therefore, I need to find the grids for S, right? Then only I can find. How I am finding the S array? How I can find the S array? S looks like this. You have stored. You have been given this value. Using this value, you find what is this value. Once you get this value, using this value, you find next. Like that, you fill this using a for loop. Yes, that's the idea. So therefore, I am storing S as a zero array. Okay, and then I can update the values in there. So see, this is the for loop. Si plus 1 is S of I plus H times f of ti comma si. Yes, that's the Euler method there. And then I am plotting here. What I am plotting t comma s with red dots. And that if there is a red circle with dot line with dashes, that is an approximate solution. If you see a blue curve, that is the approximate, that is the exact solution of the ODE. Okay, fine. We'll see. So this is how it looks. See what I am plotting here. I am plotting f of t versus t. F of t versus t. And this is my exact solution in blue. That is the curve. The solution of an ODE is a curve. Okay. So the blue curve is the exact solution, which is already known. You can easily solve this, isn't it? ds by dt equal to e to the power minus t. You can easily solve this. It is just those who don't remember the ODE. ds by dt equal to e to the power minus t. ds, take the dt here. So ds equal to e to the power minus t. Okay. Then what you do? Integrate both sides. So here you will have s equal to e to the power minus t. Integration is minus e to the power minus t. Plus the constant of integration will be the c. Okay. So therefore you put, you know the initial condition. So at t equal to 0, you will have some value. So therefore at t equal to 0, if you put it equal to minus 1, what is that value? S naught. Minus 1, right? Plus c. So c equal to s naught plus 1, right? You can put here s equal to minus e to the minus t plus s naught plus 1. This is the original solution. This is what you plot in blue. This is what is plotted in blue. Okay. And this is the red one, the approximate. Can you see that initially it was matching? Initially it matched because it is very close to initial solution. But as the time increased or as the value increased, you know, the approximation started to get error, more and error, more error. Why? Can you tell me why with the variation of x, the error started to increase? Can you see that this separation between red and blue is less than this separation? The separation between this blue and red is bigger than this separation. Why? Because you keep on iterating yi plus 1, y1, then y2, then y3, so on. Every iteration you are generating error. Every iteration you are generating error, okay? And every iteration you are storing the error again and again and again. So error builds up. Error builds up. Yes. How about, have you heard of this statement? If you say one lie, you have to say 1,000 lies again. How? If you say one lie, due to that one lie, you are telling two more lies. Telling those two more lies, you will say those 8 lies. Those 8 lies will slowly go to 1,000 lies. So why it started to spread. So therefore, keep an error and you keep on iterating the method. Due to that error, you have more error. Due to that more error, you have bigger error. Like that error keeps on increasing as you keep on iterating. Okay. And that's what exactly happens here. So Euler method is one of the very nice method that is the easiest method so far in solving ODEs. However, you can face errors because it is order of h. Okay, it's order of h. So order of h is a bigger error. Okay. So therefore, Euler method cannot work in complicated cases. Euler's method cannot work in complicated cases. It can work in simple cases. So far, we were dealing with simple ODEs. Okay. Fine. So this is the Euler's method. Similarly, you can, without any method, without any Euler method, you have to code yourself. You can use Python packages available to solve ODE directly. just you have to give the right hand side of the ODE expression. You just have to know, if you want to use Python packages, you just have to know what is the right hand side of ds by dt equal to what. That question mark here, if you know that box ds by dt equal to f, that f expression, if you know, just use the using the package, you can find the solution. We'll see how. This is known as something known as ODE int. Okay, ODE int means like you are integrating ODE. How you find y from an ordinary differential equation. If you have dy by dx equal to some function, how you find y? Because integration and differentiation are opposite things. So therefore you use the integration on the ODE so that you get the y. Yes. Anyway, so this is the idea. So from SciPy, you take ODE int, you import ODE int, okay? And this is the f equal to lambda x comma t. Now dx by dt equals to f of x comma t, where f of x comma t is given by this complicated looking equation. See how much complicated it is. It is very complicated. Okay, analytically also it is difficult to solve. 4x sine 2t minus 3x square. Very complicated. Okay, you will see. You give the initial guess. Now use ODE int, give the function that is the right hand side of the ODE, give the initial condition and tell that t, with respect to t, I want the solution. And t, if you pass t is nothing but what here? What is t here? What is t? What is t? T is an array. Array of values. Yes. That means you start from 0, then 0 to 20 I am dividing by 401. Okay. So you go in that time step. You can compute the time step. So 0, then small time step, then small time step, and so on till you reach 20. That means I am planning to solve this ordinary differential equation from time t equal to 0 to time t equal to 20. Understood? 401 means 400 values. Yes. So, okay, x naught is 0.1. That is the starting point. At t equal to 0, what is the x naught value? At t equal to 0, x naught is 1. Sorry, 0.1. Got the idea? What I'm trying, I'll try and ask randomly. What I'm trying to solve? Last. Tell descriptively. This is frying and you are not telling even. Tell what I'm trying to solve you. Yeah, what I'm trying to solve. What is the initial condition? And what I'm trying to solve? So x is a function of time. Yes. So dx by dt equal to some f of xt. Yes. So I have to give the value of t on which I have to find the value of x. What is the t? Steps. Yes. So that means at t equal to 0, I already know the value. That is 0.1. Based on that, I find what is the next value. Based on that, I find what is the next value. So Python takes the value t as an array. Okay, you can see ODE int. Where it is, yeah, here is ODE int. You give f. What is f? The right hand side of the derivative dx by dt equal to whatever right hand side. What is x naught? Is the initial condition 0.1. What is t? T is an array where you want to find the values of x. Okay, then it will base whatever value you give, it will on that set of values of t, it will find the x value. Yes, got the idea so far? Got the idea? Okay, so you can see x is that. So it will also return an array and that is stored in x. So what I have to do, I have to plot x. I have to plot x, isn't it? That's the data it has of all the ODE. Okay. So you can see that I'm plotting in orange color. Okay, fine. Okay. So you can see this solution, what I have plotted, x of t versus t. And you can see it is going from 0 to 20. What I have taken in Python, from 0 to 20 in 400 steps. Okay. Agree? Agree? So you can see that the solution is oscillating. Okay. And can you see that at x equal to y, this is correct? Anyone? This side I'll ask. Why you think that it is correct? Yeah. Why you think it is correct? Why you think it is correct? You got the solution, but how you will know that it is correct? See, you solve using ODE, but how will you know that this is the correct answer or correct solution to your ODE? Tell me. Who will tell? Wait. Who will tell? How we can check that it is correct? Mr. Jubin, how you know that it is correct? Mr. Chako, how it is correct? Chako, why it is correct? Why it is correct? Why it is correct? Initial condition is 0. Huh. Yeah, it's correct. So you check the solution at t equal to 0, you see what is the value. It is 0.1, which is already being given to your equation, which is already given in your equation, right? Which is already given to you. See this, x naught is 0.1. So if your method gives you wrong result at t equal to 0, it should not have been 0.1. It could have been some other value if it is wrong. So initial condition is correct. So therefore it is correct. So this is how, given a plot, you can see and check whether your answer is correct or not. How can you blindfoldedly believe Python and all? Just a simple observation. So similarly, you can use solve IVP. So now you know Euler method. Now we are planning to solve it using solve IVP. ODE int, you know, solve IVP. If it is an initial value problem where dy by dx is f of x comma y is given to you, and what is the value of y at x naught is given to you, initial value. You can solve it using solve IVP. Again, import solve IVP function from SciPy. Okay, solve IVP, and what you get, what you give it, again the same f value. Here, what is the value you are trying to solve? You are trying to solve dx by dt equal to cos t. dy by dt equals to cos t. How, what should be the answer? How should it look like? Can you solve this? Can you solve this? dx by dt equal to cos t. Okay. dx by dt equal to cos t. dx by dt equal to cos t. dx by dt equal to cos. Yeah. Hmm. Wait. Hmm. 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 What's the value? You but yeah. Hmm. ds by dt is cos t. What should be the value? Yes. No need to even open the notebook. What you did, put the derivative so that you get cos t. Should click your mind that sign. Derivative taking differentiation of sine is cos. So sine t should be the solution. So if your answer is correct, you should get sine t. The curve should be sine t. You know sine t how it is. Yes. So solve IVP, you give that function, you give the range on what you want to find. 0 to pi. 0 to pi. You see how from 0 to pi your sine function looks like. Yes. Fine. And the t equals t equals to t eval. That is in this range I want to solve. And just it, you have to store in sol. Okay. And you are printing sol.t. Fine. This is the solution you get. Okay. Can you see why it is correct solution? Okay, you got the solution printed in Python. Why it is the correct solution? 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 Hmm. Why it is correct solution? Why it is a correct solution? Why it is correct solution? Why correct solution? Why correct solution? Why correct solution? Why correct solution? I could not hear. Again tell. Good. Why could not tell? You will see the initial condition. At t equal to 0, s is 0. And even at pi, you can check. At pi by 2, which is like, pi by 2 is like 1 point something. 1 point, huh? 1.5. Pi by 2. What is the value of pi by 2? Yeah, here it is 1. Okay. So that you know that correct. Okay. Okay. So I hope you got an idea like how we can use Euler method. How we can use Euler method, that is this method. So what we learned so far, we used Euler method. Then we used we saw using Python we saw using Python how to solve Euler method, any equation, any complicated equation. Okay. Then what are the packages in Python we learned? Solve IBP, ODE, and anything else? Yes, you can just directly code it using for loop. Okay, Euler method. So these all things we learned so far, how to do in Python and also using Euler numerical method. Now we need to go to a new numerical method, that is Ranjakutta method. Okay. So this is known as Ranjakutta method, or RK for short. Ranjakutta method for solving ODE, RK4 method. So what you do, we will not prove anything here like we solved for Euler method, but I will give you an idea how this works. So remember that Euler method started. How Euler method started? Euler method started by taking the initial condition, by taking the slope, approximating the slope. Okay, isn't it? That at given point, at the starting point, you take the slope and approximate what is the value of slope. At every iteration, you approximate the slope. That is how Euler method works. You take the approximation of the slope as the new solution. That's how Euler method works. Okay. But Ranjikutta method works even more better. Okay. How it can work better? So it works adaptively. It works adaptively. Rather than taking at every iteration, you take the weighted average of multiple steps. Okay. So we'll not go into all the details, but I'll just give you the iteration mechanism behind RK4 method. Okay. Fine. So this is the most commonly used method, especially in Python, or if you want robust solutions to your ordinary differential equation. Okay. However, you do, like, you can know that anything changes with time is a ODE system. Okay. Recently a news came where someone like in the US, they solved the aerodynamic problem. Okay, aerodynamic problem. It's a 400-year-old problem, and they just solved it recently, which can make use of that ODE to solve the noise in the aeroplane when it is flying. There is a cluttering sound in the aeroplane when you fly. Yes. So how to reduce that sound? So those are modeled using ODEs itself, and PDEs also. Okay. So they used all this numerical method scheme to find and detect where the error was coming from. And then they tried which method or which sort of modeling we can do so that it can reduce that error. She is a lady who solved this problem. Okay. So, so you can see any scientific domain you go, ODEs will be there. Okay. So the most commonly used method is the Ranjikutta method, and most we will see the first is the fourth order method, without going into the derivation how it is derived. But from now on, the method will be a bit more complex as we move on. Okay. So I suggest you keep the patience and try to understand this. As usual, what should be our target? Y, to find the value of y. If given dy by dx is f of x comma y, our target is to find yi plus 1, depending on yi. Okay. And then slowly at each evaluation step, you find yi plus 1 so that you cover the time domain and find all the solutions. That's the idea. Okay. Now, what is yi plus 1 for the fourth order Ranjikutta? Those who already learned can tell. Okay, I will write it for you. Yi plus 1 is obviously depending on yi, fine, plus there is something unintuitive that you are taking a weighted average. So you will see a big expression here, that is 1 by 6. 1 by 6 times k1 plus 2k2 plus 2k3 plus k4. Okay. Now what are these k1, k2, k3, k4? Okay, so you can see, just I will tell you one more thing. Observe these numbers: 1 times k1, 2 times k2, 2 times k3, 1 times k4. Now, what is the sum of 1, 2, 2, 1? 6. And you can see that's how it is a weighted average. You are dividing by 6. Okay. Now the question is, what are each of these ki's? What is k1? Okay, k1 is h, the step size multiplied by the function value at xi ya. Okay, what is k2? K2 is h multiplied by a function value evaluated at a different set of x and y, that is xi plus h by 2, comma yi plus k1 by 2. So k2 depends on k1. K2 depends on k1. So first you evaluate k1, you note the value, then you put in the expression of k2 to get k2 value. Okay. What is k3? K3 is h times f of xi plus h by 2, comma yi plus k2 by 2. So k3 depends on k2. You are seeing the pattern, I hope. Okay. So what is k4? K4 is h times f of xi plus h, comma yi plus k3. So you can see that k1 you solve independently, h times f of xi ya. Okay. So if you only consider k1 and nothing else, if you only consider k1, it is just like Euler method. If you only consider k1, it is just like Euler method. Okay. Then if you consider k2, k2 depends on k1, k3 depends on k2, k4 depends on k3. You can see the iterative method happening here. Okay. Fine. So this is the fourth order Euler method. Okay, fine. So I suggest that we solve one question based on this method so that you can know how to use this method. Okay. Then we can see this in Python, how to solve this. Okay. So I suggest the same question. We will have the same question here. Dx by dt equals to 1 plus x over t. Okay. And you have the initial condition x of 1 is 1. So I suggest you take the step size of 1 and use RK4 method. Use RK4 method to find the solutions. And compare with Euler, which you already solved before. So, iteration 1, I will go with you because it's a new method. Iteration 1. So, what you will find with iteration 1? Have I solved it here? No. Okay. Iteration 1. So, what should we finally do? Compute ki's. What is k1? Okay. What is y1? Y0 plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. Agree? Yes. Now you tell me what is y0? I think I wrote mistake here, right? We should not write y, right? We should not write y. Rather, we should write what? X1 is x0. Okay. So what is x0? X0 is 1 plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. Now what are the ki's? That's what we have to find. So what is k1? H. H is 1. 1 times f of. So this is f of x comma t, right? Yes, t comma x. Good. Good. Yes, so 1 times, check the notes on the left. Yes, f of x, t comma x. So what is t comma x? 1 plus x naught by t naught. That is equal to 1 times 1 plus 1 by 1. That is equal to 2. K2 equals to h. H is 1. F of xi. Xi means x naught plus 1 by 2, comma y naught plus k1 by 2. K1 by 2 is 2 by 2. So that is equal to 1.1 times f of x naught plus half, comma y naught plus 1. What is this value? X naught is 1. X naught is 1, right? What is x naught? What is x now? So f of 3 by 2, comma, y naught. Sorry, instead of y naught, it should be t naught, right? Yes, t naught. What is t naught? T naught is also 1. T naught is also 1, right? So 2. So what is this value? F of 3. Oh, f of t naught, comma, oh, it's alternate. Okay. Yeah, I should have written it as f of t naught plus 1, comma, x naught plus 1 by 2, right? So what is this value? F of 2, comma, 3 by 2. What is this value? Yes, what is this value? Yes. Again? Is there a mistake? Where? T naught plus? Yes. I think, yeah, we cannot interchange because the formula also changes. We'll write again. So K2 is H times F of Xi. Xi plays the role of T. So you have what? T naught plus 1 by 2, comma, X1 plus 2 by 2. So this is F of 3 by 2, comma, 2. Isn't it? Agree. Correct, right? So what is this value? So this is T, this is X. So you have to put 1 plus X by T, right? 3 by 2 divided by 2 by 3 by 2. 1 plus 4 by 3. 2.333. No, 2 by 3 by 2. X by T. This is T, this is X, right? Okay. What is K3? What is K3? H times F of X, F of T naught plus 1 by 2, comma, X1 plus K2 by 2. That is 2.333 by 2. What is this value? This is T naught is 1, right? So this is T1 plus 1 by 2, comma, X1 is 1. X1 is what? Sorry, this should be X naught, right? This should be X naught depending on the past value. X naught is 1 already. 1.2.333 by 2, what much, how much you are getting? 1 plus this whole thing. 2 point F of 3 by 2, comma, 2.1665. So this is what? 1 plus X by T. So this is 1 plus 2.1665 divided by 1.5. Yes, what is this value? Calculator. Keeping in calculator in bag, and then you are thinking you will solve RK4, is it? 2.11. Okay, what is K4? K4 is 1 times F of Xi plus H. Xi is X naught is 1. Yes, sorry, T. Again, tell me the step. Tell me the step. Is it? Who told me 2.1? So this guy should be F of T naught plus H. T naught is 1. 1 plus 1, comma, yi, that is 1 plus k3. K3 is 2.44. So this should be f of 2 comma 3.44. So this should be 1 plus 3.44 divided by 2. So it should be yes. Okay, so K1, K2, K3, and K4 we got. Okay, now what should be our step? Keeping all these things in mind, what should we solve? Keeping all these things in mind, what you need to solve? Yes, y, I plus 1, that is y1 is equal to y naught. What is y naught for you? Sorry, I again messed up with the notation. Yes, x, right? x1 is equal to x naught plus h by 6, sorry, 1 by 6 into k1 plus 2k2 plus 2k3 plus k4. So x1 is equal to x naught. You already know it is 1. 1 by 6 times k1. What is k1? 2. 2 times k2. What is k2? 2.333 plus 2 times k3. 2.44. What is k4? 2.722. Can you tell me this value? What should be the value? 3.3798. Okay. Fine. So this is how you got the value. So what is x1? x1 means x at t equals to 2. Because you at t equals to 1, we have x equal to 1. And you have solved using h equal to 1. So the next time step is, this is t naught. This t1 is 2. So this is x naught. At t naught equal to 1, we have x naught equal to 1. Okay. So at t1 equal to 2, you will have x1 equal to, using Ranjagutta method, is equal to 3.378. That is the solution. So without solving the ODE, you solve this. Okay. Can you check this with the Euler method? What you are getting? I think you did not solve using Euler method at t equal to, at using h equal to 1. You solved using h equal to 0.1. So in order to get to at t1 equal to 2, you have to solve the Euler method in 10 steps, where you did only one step here. Can you understand the powerfulness of the RK4 method? Look back into your previous notes and compare with this. You will understand the power of RK4 method. And explain me. Some of you asked the question that if I put, instead of h equal to 0.1, I put h equal to 1 in Euler method, then will I get the same solution as in RK4? How many of you think yes? Put. Now those who are saying yes should put and check. 3. Yes. So you can see that there is an error. There is an error of 0.3, which is big. If you're, you get nearby, but why you don't get nearby? So 3.37 you are getting in RK4 method. Of course, there will be huge error if you take h equal to 1. I told you that Euler method is a order h method. The error will be of order h. I told you here, right? You can see. I told you if you increase h, error will be bigger. Here I already told. So when you took h equal to 0.1, your error was small. You take h equal to 0.1, take 10 steps and solve the same. And then take h equal to 1 and solve using one step. You will see the difference. Okay. So using h equal to 0.1, even you will get better than this. More than 3 you will get. Where you took h equal to 1, bigger h, you landed in 3, that is giving you large error. Okay. So you can see this is the actually the accurate answer 3.378, because RK4 is a very nice method. Okay, like it will give you much more accurate than any other. Okay, happy with this? Okay, got the idea. I hope you got the idea. So similarly, if it is being asked to you that solve for T2 equal to 3, then yes, you have to do 2 iterations of RK4 method. So this can come. Okay. So you have to understand the steps. Okay. Nothing is there much. You need to know what is the formula for RK4, that you need to understand. Like you are taking a weighted average 1, 2, 2, 1 and dividing by 6. And K1, K2, K3, K4, you understand the pattern. K1 is just like Euler method, h times f of xi comma yi. K2, h of xi plus h by 2 and also depends on K1. K3 depends on K2. Okay. And K4 depends on K3. So that is the method of RK4. Okay, fine. This is RK4 method. Now you can also do the same with RK2 method. Okay. Now what is RK2? RK2. What is RK2 method? So it is a second order method. Second order method. RK4 is a 4-order method. RK2 is a second order method. So what is RK2 method? So you have again yi plus 1 is yi plus h by 2 times, maybe I should wait. We will follow the same notation. Yi equal to yi plus 1 over 2 k1 plus k2. Can you see the difference now? It is still a weighted sum. Why it is a weighted sum? Because you have 1 times k1, 1 times k2, and then you are dividing by the sum of the weights, 1 plus 1, that is 2. It is a second order method, so you have k1, k2. If you have a 4-order method, that is RK4, you will have k1, k2, k3, k4. You got the pattern? If you are with RK4 method, you have k1, k2, k3, k4. And then you have to take 1, 2, 2, 1 and divide by 6. If you have RK2 method, you will have k1, k2. K1, K2 of equal weights, 1 and 1. Therefore, you are dividing by 2. Now, what is K1? Where K1 equals to f of xi comma yi, h times f of xi comma yi. K2 equals to h times f of xi plus h comma yi plus h times K1. Okay. So I suggest write the RK2 method and RK4 method side by side. Okay, and see what is the pattern you are getting. So it is following the method of weighted averages. Weighted average. Okay. Now can you solve this using RK2 method? Try to solve that. Solve that same problem using RK2 method. Yes. Solve the same problem using RK2 method. So many of you have already solved. So I will just write the answer here, like, okay, K1 is just one line step, one line computation. What is K1 you are getting? What is the value of K1? K1 you are getting as 2, K2 you are getting as 2.5. Yes. So therefore, y1 equal to y0, which is equal to 1 plus 1 by 2 times 1 times K1, that is 2 plus 1 times K2, that is 2.5. So therefore, you are getting how much? 1 plus 1 by 2 into 4.5, which is equal to 1 plus 2.25, 3.25. Okay. So you can see the same value you got using RK2 method. Using RK4 method, what value you got? 3.378. Using Euler, what you got? So you can see which one is better. You can see RK4 has always turned out to be better here. How you know? You can solve this. This is not a very difficult differential equation. You can just solve and compute what is the actual case, and you will see that RK4 wins. Okay, fine. Now, I hope how many of you already have learned this method before? This one, RK4. Someone told they have already. Tell the truth, what? Without truth, how justice will exist? That is this. How many of you already learned about RK4 method before? Many people, someone. Anyway, so as I told you in the beginning of the class, so far you have solved differential equations of the form dy by dx is say e to the power x or e to the power x square, something like that. So far, dy by dx. But how you can solve coupled ODEs, coupled linear ODEs? So that is what I hope no one has taught you so far. And that's what is the last part of this module. Okay. Accordingly, the Ranchakutta method will be a bit complex, but I hope that we will solve it in the class. I want you to solve so that you will know how to do it. Of course, the notation is going to be very much complicated. The notation is going to be complicated, but at least you will know how to solve the coupled ODE. I want you to learn that. Okay. People have learned so far. See, in any course, people usually learn about Euler method. People usually learn about RK4, RK2 method. Okay. But people usually skip the coupled ODE part, which I think is necessary. Always you don't really get the ODE of this form. It can be a coupled ODE also. What do you mean by coupled ODE? My question is exactly the same. How can you solve this equation? This is a coupled equation, isn't it? dy by dx is x plus z. dz by dx is y minus x. This is a coupled ODE. Why is a coupled ODE? Y varies with respect to x as the variance depends on both x and z, and at the same time z is varying as dz by dx is y minus x. So you can see that it is a coupled ODE, isn't it? Okay, to understand better, I will give you one more example. dy by dx is 5. dz by dx equals to 6x, or say, yeah. Is it a coupled ODE? It is not a coupled ODE. Why it is not a coupled ODE? Because y dy by dx is varying constantly. Okay, y is not depending on z, and z is not depending on y. That's how it is coupling. So you can see this is not a coupled ODE. How many of you understand this or did not understand? Did not understand. Okay. Yes. Suppose your name is Milan. Yes, Milan. So Milan is riding in his bike. Okay. So let us draw. So Milan is here and his bike is here. Okay. This is his bike. Okay. So this is Milan and this is his bike. Can you survive without your bike? Well, you need your bike. Is it? So you depend on bike. Okay. Now, does the bike depend on you? Yes. Bike depends on you. If you don't use the bike, who will use the bike? It will just lie there and it will get rust. Yes. No petrol, nothing. Every time rain, gone, right? If you are there, you will take it into a shade. If no one is there, who will take it? So therefore, bike also depends on you. So that's it is a coupled system. Similarly, husband and wife. It's a couple. Husband depends on wife. Wife depends on husband also. Okay. So they, yeah. So they combine that methodology in such a way that the system runs in a stable way. So therefore, in the same way, here it is coupled ODEs. Coupled ODEs. What do you mean by coupled ODEs? Coupled ODE means Y, the variation of Y. This is one system. This is another system. Now the question is, does system 1 depend on system 2? If it does, it's a coupled system. If system 1 doesn't depend on system 2, it is an uncoupled system. Now my question is, this is the question. Does system 1 depend on system 2? How? How can you say? Because Z is there. Okay, Z is there and variation of Z is occurring in the second system. So if this guy doesn't vary properly, it affects in this system because Z is there. So therefore you can see the connection between these two. So therefore it is a coupled system. But see this, for example, this is another question. dy by dx is 5. It is not depending on Z. So this guy doesn't depend on this guy. So these two are uncoupled systems. Can you see the difference now? Coupled and uncoupled. Coupled means system 1 depends on system 2 and system 2 also depends on system 1. Does system 2 depends on system 1? Yes. System 2 depends on X. Sorry, depends on Y and Y is varying. So therefore system 2 also depends on system 1. Can you understand? Can you understand why this is a coupled system? Ms. Durga, understand why? Harilal, you can. See. I don't know why I get confused. Sri Hari, yes. How one system take dy by dx, where it is depending? Louder, louder. Here you tell. Then tell us that Mr. Samuel can hear. Tell in way. Well, stems. Look, that's it. Tell. Tell. Tell to Samuel. dy by dx is depending on second system, but dz by dx is not depending on. And the 5, 6, 6. Durga, you tell Samuel to you tell to Samuel. How second equation also depends. So I hope you understood. Okay. So our aim in this class, is to solve this coupled system. Our aim in this class is to solve this coupled system of ODEs. Okay. So for that, I think we can use both RK2 and RK4 method. Okay. Maybe it is going to be a big method. Shall we cover it in next class? Maybe we'll cover. Okay. Okay, what we will know in next class, I will just sketch a outline what we are going to cover in next class. Next class, we will solve this differential equation which depends on both variables. That means dy by dx, sorry, dy1 by dx is a function of x y1 y2, and dy2 by dx is a function f2 of x y1 y2. Okay. Here also given that y1 at x naught is y naught, y1 naught, y2 at x naught is y2 naught. These are the initial conditions. Our job is to solve this using RK2 and RK4 method. Okay, this is our job next class. So you will see that the function definition for both RK2 and RK4 method will change. It will involve not only KIs, but it will also involve LIs. Okay, so these are the final cases. We will see, and this equation, that is dy by dx, where it is, yes, this equation we will solve using both RK2 and RK4 method. After this, we will go to PDEs. After this, we will go to partial differential equations. What are the different types of partial differential equations and how to solve PDEs. Okay, maybe depends on the method. If it is a heat equation, how to solve it. If it is a parabolic PDE, parabolic PDE. If it is what is a parabolic PDE? What is an elliptic PDE? How to solve parabolic PDE? What numerical methods are there? For elliptic methods, what numerical methods are there? What is Crank-Nicolson method? All these things we will see. Okay, how to divide the domain into grids and solve the method. So that will be the PDE methods we will discuss so far. And that is it. Okay, ODEs and PDEs. Fine. Okay. So I hope it is okay. Okay.